All right, in this video, I'm going to show you how to measure the orbit of a moon going around a planet. Let me share my screen. Okay, here we are in Afterglow, and I've already gone ahead and loaded in a series of images, in this case of the planet Saturn. And these were collected as part of a single observation, a repeating observation, that we set up to repeat once a day. And most of these images were collected by the Prompt 5 telescope in the Chilean Andes, though a few of them were collected by our Prompt Meckering telescope in Western Australia. Now in this lab, you're supposed to pick one currently observable gas giant, so Jupiter, Saturn, Uranus, or Neptune, and collect this series of data. And depending on which planet you chose, there's a particular moon that we want you to track. And that moon is listed in the lab. In the case of Saturn, the moon is Titan. So one of these points of light around Saturn is Titan. We'll figure out which one in just a bit. And as I go from image to image to image, we'll see Titan and the other moons move around the planet. So what we're going to measure is how far is our particular moon from the planet, and how does this separation change with time. So from each image, there are two things that we're measuring or finding. One is when was the image taken, so the time, and the second is the separation of our particular moon from the planet. Now it's easier if we just get all the times first and then come back and measure all the separations. So let's start with the times. And you may remember from lab 1 that we can get the time that an image was taken from the file info tab over here on the right with an I. So if I click on that, you can see some vital information about that particular image, including when the observation was taken. And here it's written out in year, month, day, hour, minute, second format. And that's not going to be the most convenient format, because in the next video, what we're going to do is we're going to plot the separation as a function of time. And to do that, we have to get the time into a single number, like 2019 point something, something, something. And what you could do is you can convert the seconds to minutes, minutes to hours, hours to days, days to months, and months to years to get it into that decimal format, but that's a bit of a pain. So instead of using this timestamp, we're going to use something called the Julian date. And eventually, we're going to put it on the screen. So you should be able to find it on this short list. But if it's not there, you can always look at the full header information. And you can see that by coming up to the top and flipping the switch. So there's a lot of information here. A lot of it's very technical information about your image, about the instrument that was used to collect it. We're just looking for JD. Here it is, JD, Julian date. It's a long number. It's measuring a number of days, and you can see it's already in a decimal format. So for this first image, this is the time that I want. So I'm going to highlight it, copy it, and I'm going to go paste it into an Excel spreadsheet, or anywhere that you want, just to record it, and we'll come back and use it later. Then I'm going to go to the next image, and I'm going to find JD in this list. It's here somewhere. There it is. JD, copy, paste. Go to the next one. Here it is, copy, paste. And I'm going to record that for all of the images in my sequence. Okay, now I'm going to go back to the first one, and we're going to measure the separation of our moon from our planet. So a couple things to do here. First, let's see as many moons as possible. And you may remember from lab 1, the way to do that is to change the saturation level. So here's the saturation level as a percentile. As I increase that number, the sky glow around the planet decreases, I can see moons closer in. If I go too far, I'm going to lose some of my moons. See, they're getting too faint to see. So I have to strike a balance. Keeping that sky glow as small as possible, I'm still able to see many of the points of light around the planet. Now you can do this individually for each image, but that's kind of a pain. So if you come over here to the gear and just select this, Sync Display Settings, then come back, you'll see that now every image has been reset to that saturation level. Now you can go in and adjust individually if you want to, or if you need to, but that gets them all approximately at the right level. Okay, back to the first one. Now the next thing we need to do is figure out which of these points of light is Titan. And this is also something you learned to do in Lab 1. So we're going to open up Stellarium, and we've gone through these steps before. I'm going to come up here and make sure that I'm in Universal Time, UTC, Daylight Savings Time turned off, and I am, so that's good. I'm going to come down here and turn off the ground and turn off the sky. I'm going to come over here and find Saturn. Zoom into it, either with the scroll wheel of your mouse, the page up, page down button. And finally, I'm going to orient it the same as my image by pressing the telescope icon. Okay. Now we're good to go to compare these to our images. We just have to change the time. So I'm going to slide this off for a second. I'm going to come back here to the File Info tab. So this is the time that this particular image was taken. I'll bring Saturn back up, and I'll come over here and change the time. So this image was taken in 2019, October 17th, 00:50. The seconds don't matter. I'll get rid of that and scroll out a bit. I don't see Saturn, so I'm just going to search for it again. There it is. Okay. So this should match up fairly nicely with my image. Again, you can click off the planet if you want to get rid of those words and gain yourself some space. If I slide this over here, you can see the pattern matches. We have these two, Dione and Tethys. Enceladus, I can't really see. It's lost in the sky glow, same as Mimas. But here's Rhea over here. And then lastly, we have Titan. Maybe I'll scroll out a little bit here. Rhea and Titan, Rhea and Titan. So this one out here, the bright one, which makes sense since Titan is the largest moon of Saturn, that is the one that we want. Okay. So how do we measure the separation of this from that? So we go over to the ruler tab, and I'm going to use the centroiding. That means we don't have to click exactly in the middle. Afterglow will figure it out. We just have to get close. So I turn on the centroiding. I go to the moon first and get as close to the center as I can and click it. And then you see we have a measuring bar. And now I'm going to come over here and click planet centroiding. When you centroid on a planet, the planet's broad and extended. And so there's a different algorithm to do the centroiding. So I click on planet centroiding, click somewhere in the middle here, and you see how it shifted it to the exact center. And then I get the separation, and it's down here in arc seconds. 113.338. So I'm going to copy that and paste that into my Excel spreadsheet. Okay. Now I'm going to go to the next image, do the same thing, and at first it may not look exactly the same. In one day, the moon shouldn't move too much, but in this case it doesn't look the same because the image is flipped, and let me demonstrate that to you. So I'm going to come back up here to the File Info, slide this over here. I'm going to update the timestamp. This was done This one's actually only 12 hours later. So in that time, the moons have moved a little bit. See, these two have gone a little bit farther down. These two are swinging around over top. I compare that to this, and it's pretty clear that this image just needs a rotation. So I'm going to clear this over here, come back up to the top. I'm going to press the rotate button twice. Sometimes you'll need to rotate your image to make it match up. That's a good match. So indeed, that is Titan. So again, I'm going to measure the separation using the ruler tool. I'm going to turn off planet centroiding to click on the moon, and then turn it back on to click on the planet. Then this separation is 90.654. I'm going to copy that and record it in my Excel spreadsheet. And then you keep doing it from image to image to image. We had a couple of flips there, but here you can see a nice sequence where they're all oriented the same way. And see how Titan is moving? These last few, I haven't looked at them yet. So that one's flipped. Let's go back, I think it was to here. So Titan is this one here. And as I go from image to image, you can see its motion around the planet. And then this one's flipped. This one's back to the normal orientation. And same with this one. So you shouldn't have to consult Stellarium every single time. Though if you do lose track of where you are, or if the image is actually not flipped, but rotated by 180 degrees, you may have to use Stellarium to get your bearings back. Okay, and then save all that information onto an Excel spreadsheet or a spreadsheet of some type, and then we'll pick up from here in the next video.